We had just found a size of 14 by 24, a little larger than our guessed size of 12 by 24. And because of that, we updated the self-weight slightly higher than we had guessed earlier. And because we had new self-weight, we had new dead WD stay the same. The live stays the same, but the WU changes and the moments change slightly. They're slightly bigger now. These are our new moments, and now we need to calculate the steel. I'm just going to do them positive and negative. This is a key thing. In the negative moment, B is 14. So again, let's try to remember this. Let me see if I can draw this nicer. Struggling here. Anyway, here we go. Try it again. There. Okay, good enough. Okay. Okay. In the negative moment, this is the compression zone, and in the positive moment, that's the compression zone. B is 14 for the negative moment, B is 60 for the positive moment. Okay. These are the updated moments we just calculated. Divide by 0.9, multiply by 12, and you get MN required. And so this is MN over BD squared. So that's going to be 14 times 21.5 squared. This is going to be MN over 60 times 21.5 squared. See how small that is after you plug it into the equation, the RN equation? That's the 1.07 was what we had originally guessed. This is rho times BD, which is 14 times 21.5. This is rho times BD, which is 60 times 21.5. And you get 1.42 for the positive moment and 3.10 for the negative moment. And you can see that the difference in the steel, well, it's mostly because the negative moment's about double the positive. Well, it's exactly double the positive moment for my assumption. Okay, and I ended up picking two number 11s for that, two number 8s for that. This is just slightly bigger than 3.1, so we would expect VMN to be very close to MU. The closest one I could pick was this. It's significantly higher than 1.42, and we should have VMN quite a bit bigger than MU. Let's double check everything. Plus, I want to show you how to calculate the MN. Let me copy this and bring it there. Copy. Let's put that down here so we can see what we're doing. Okay. In this case, we had for negative moment up here, two number 11s. And for the positive moment down here, tension on the bottom, to number 8. Okay. There's the area of steel, looked it up in the table. B is 14 inches, negative moment, compression on the bottom. Positive moment, B is 60 inches. T is just Fy times AS. And you do T equals C, solve for A equals T divided by 0.85 F prime C B. And it's because it has the small b, you get a larger A. B, remember, is 60 inches. You get a very tiny A. only half an inch compression zone because the width is so high. Z is D minus A over 2. And even though it's the same beam, there's a slight difference in the Z because of the wide width of the compression zone in positive moment. And so A is smaller, Z is bigger because it's D minus A over 2. And this is what I mean by saying the beam is more effective in positive moment than negative moment. M is T times Z. Phi is 0.9 and divide by 12 to get foot kips. And just reminding us that was the MU, that was the MU. And to see how much over we are, yeah, this is within 1%, and this is like 10% over, and we're done. And if you were born before 2005, you don't know what I'm talking about, you can go look it up. It's funny, sort of. And finally, what you would have to do is make a sketch of the whole thing. I'll leave that to you. Okay, this closes out the flexure portion of our course.